Welcome to Jonathan's Comfy Chem Corner. Glad you could join me. I'll be talking about ionization energy and electronegativity. Ionization energy is basically the amount of force needed in order to take away an electron from an atom. The more up and to the right you go on the periodic table, the higher the ionization energy will be. So if you go to the halogens there, for example, chlorine, it's not going to want to give away an electron, so it takes a lot of energy to take it, because it has nearly a full valence shell. It's much rather steal something than give away something, so it's going to say no, no, no. And also everything's very close and attracted to the nucleus, so it's going to be hard to peel something away, unlike francium, where that one electron in the very end that's sitting lonely on the very last valence shell, he's all alone and nobody's watching him. You can just snatch him up in the night. Electronegativity is how willing an atom is to receive an electron, so kind of the opposite of ionization energy. Instead of taking something away, how much does an atom want to get another electron? So that would be the swap here. Francium wants to give away that little boy on the very end. It's being pushed away by all the other electrons and all the other valence shells away from the nucleus. But chlorine desperately wants another electron, so it will snatch that little man. So they can both be happy with full valence shells. Noble gases don't have electronegativity because they're already happy, perfect little elements. They have full valence shells and they have no need to give away or receive another one. Be nearly impossible to do that because of how attracted the electrons are to the nucleus.
In this segment, we're going to be looking at atomic radius. Atomic radius is basically just the size of an atom. So with trying to find the size of an atom, you're going to need a periodic table of elements. So the more right you go, so this way on the periodic table, the smaller the atoms get. So lithium is bigger than neon, and sodium is bigger than argon. And the more downwards you go, the bigger your atoms get. The reason they get bigger when you're going downward is because more quantums are being added, more rings around the atoms are being added. And the positive force from the nucleus can't grab all these atoms and bring them close together because they're getting farther and farther away. And why they're so tight and compact over here is because the charges from the protons get bigger. So when a proton like neon, which has, an atom like neon has 10 protons, the pull is much greater. So having 10 electrons and having 8 electrons as valence electrons, they can be pushed in and scrunched in easier. I'll give an example right here. So right here we have a blank canvas, and I'm gonna make some element that's really big. So I think I'm gonna choose lithium. So with lithium, it has 3 protons in the middle, so we're gonna need 3 protons around it. So why this atom's bigger than the rest is because lithium has a charge of 3 and has 3 electrons, but this one electron right here is not getting pulled in as much as these 2 right here. So this electron is getting pushed out because of these 2 negatives, and the pull from the +3 is not strong enough to pull this one in. So it has to go out more, and it's pulled out even more. And these 2 atoms are kind of like a barrier, and the negative charges from this are pushing it out. And next we'll be looking at fluorine. Fluorine is also a very small, it's a small element. It's not like neon, but it is pretty small because it has 9 electrons, and those electrons, 7 of them are valence electrons. So right here I'm gonna bring in our fluorine atom. So fluorine has 9 protons in the middle with 9 neutrons. So you're gonna need 9 electrons as well. And 9. So with these 9 electrons, it's a lot more compact because fluorine has a stronger pull towards all these electrons, and these two electrons in the middle aren't pushing all these electrons out. There's more of a power of pushing in. So this grabs everyone and brings them closer together. So that's why fluorine is smaller compared to lithium, and that's how atomic radius works.
Good evening, boys and women. Today we will be talking about ionic bonding and covalent bonding, but first, can we get 5 likes on this video? It would make Papa very pleased. First, we'll start with an ionic bond example, which is a metal and a non-metal bonding together. We're here using fluorine and lithium. Fluorine is one away from having the full valence shell, and lithium wants to give away one of its little baby boys. So fluorine's just going to eat that one up, and they're both going to be happy in this case. Then for our covalent bond example, we'll be using H2O, which makes everyone happy and also keeps them alive. We have oxygen here, which needs 2 more electrons to have full valence shell, and the 2 hydrogens here will provide that. Now this is also an example of a polar bond. Oxygen is attracting the electrons way more than the hydrogen, and they create an opposite charge where oxygen is negative and the hydrogens are positive. The 2 elements unequally share the electrons, but share it nonetheless.